In this tutorial, I am going to discuss a programming question to remove nth node from end of linked list. So the problem statement is given a single linked list. We have to write a code to remove the nth node from the end of a linked list. And you can assume that the value of n is always valid. So this is the input linked list in which 4 nodes are present, and the value of n is 2, so we have to remove second node from the end of a linked list. So this is the first node and this is the second node, and once we remove this node from the linked list, we get following output in which only 3 nodes are there and this node is removed. So if you see the input linked list, so head points to this node has the address of next node, and this node has the address of this node, and this node has the address of this node. But once we remove this linked list, what does it mean? It means this node points to the address of this node instead of this node. The node this node will points to the address of this node. So this node will be automatically removed. So this is the problem statement, and now let's discuss the multiple approaches to solve this problem and their time complexity. So let's discuss our first approach to remove nth node from the end of a single linked list. So to remove nth node from the end of a single linked list, we have to know the number of nodes present in a linked list so that we can compute that we have to remove the node from this position. So our first step is to count the number of nodes present in a linked list. So let's say first we have to do the one traversal to count the number of nodes. So let's say in this case, the value after this traversal we get the value 4. So we know the number of nodes present in this linked list is 4. Now we have to remove the nth node. I mean, so then we have to calculate the position. So position is, so this is the fourth, so the length is 4. So there are 4 nodes present in a linked list, and the value of n is 2, and then we do plus 1. So we have to remove the third node from the beginning. So this is first, this is second, and this is the third, and this is the second node from the end of a linked list. So we have to remove this third node from the beginning. So what we have to do is we have to traverse this linked list again, and we have to reach at this position, and then we have to make, I mean, we have to assign the address of this node to the address of this node so that we can remove this node from the linked list. So so uh, so this node points to the address of this node. We have to, I mean, break this link, and we have to assign the address of this node to this node. So what we do is, so this is the special case. Let's leave this case as of now, we come back later. So let's focus on this code. So in this code, what we are doing is uh, we we are again traversing a linked list, and we are in, so we reassign the value of length to 0, and we are incrementing the value at each step. And we so this is the condition. When we reach at this step, let's assign the address of this node to this node so that we can remove this linked list. So let's dry run this code. So so temp will points to the address of this node, and the value of length is 0. So now uh, let's start traversing, and the value of length is 1, and so this condition is not true. Position minus 1, so the value of position is 3, and minus 1 it is 2. Is it equal to length? The value of length is 1. No. So let's move to this statement, and now the temp will points to the address of this node. Now again the value of length is 2, and So this condition is true this time, so position minus 1, so the value of position is 3 and minus 1 2, so it is equal to length. So what we do is we assign the address of this node to this node, and then we go back, we move, we execute this statement, and we keep repeating, this while loop continues uh, until the temp does not points to null, and after that we return head. So once we done with this step, we get this linked list. So the 15, then we have 9, then we have 5. So we have removed the nth node from end, and then it points to null, and the head points to this node. So what about, so we use two traversal in this approach. First, we count the number of nodes present in a linked list, then in second traversal we reach at that position, we make, we delink this node, and we assign the address of next node to the previous node, and then we return this head pointer. So the time complexity of this approach is O(n), and its space complexity is O(1). So we used only constant space. So what about this special case? So this is the case. Now suppose we have a linked list in which only one node are present. So let's say head points to this node, and this node points to the address of this node points to null. So only one node is present in a linked list. So in that case, if we have to remove this node, we can simply return head dot next. So in this case, we after removing this node, we get null. So this is the special case, and it is the handling of that case. So in this approach we use two traversal, and now in the next approach, let's see how we can solve this problem in a single traversal. Let's see how we can optimize our previous approach. So in our previous approach, we solved this problem using two traversal, and let's see how we can solve this problem in a single traversal using two pointers. So what we can do is, let's declare two pointer, fast and slow, and both fast and slow pointer points to the address of first node. So the next step is to move the fast pointer by n step and keep the slow pointer as it is. So let's move the fast pointer. So the value of n is 2. So let's move the fast pointer by 2 step. So first fast pointer will go at this node, and then the fast pointer will point to the address of this node. So after moving fast pointer by 2 step, the fast pointer will points to the address of this node, and slow pointer so we keep the slow pointer as it is. Now we have maintained the nth distance between two pointers. The next step is to move both the pointers by one step until the fast pointer does not points to null. So let's move both the pointers by one step. So let's move fast pointer, and after when we move fast pointer by one step, it points to the address of this node, and when we move slow pointer by one step, it points to the address of this node, and in next iteration fast pointer points to null. So we came out of this loop, and you can see when the fast pointer reaches the end, the slow pointer will be exactly nth node from the end. This is why we move fast pointer by n step in the beginning. So this is the reason for moving the fast pointer in advance. And now this pointer points to the address of this node, and we have to remove this node. So this is the second node from the end of a linked list. So what we have to do is, so we have to assign the address of this node to the address of this node. So you can see this statement. So in this statement we are assigning the address of this node to the address of this node, so that we can remove this node from the linked list, and after that we return head. So once this operation, we do this operation, the linked list will be like 15, then it points to the address of this 9, and then it points to the address of this node. So instead of a node whose value is 8, it will points to the address of this node, and 8 will be removed, and head will points to the address of first node. And what about this code? We have not discussed this code. So now suppose in a linked list we have only one node. So basically let's say we have only a node 15, so only one node in a linked list, and head points to this node, and this node points to null. So it's the only node in a linked list, and we have to remove uh, first node from the end, so from the beginning or from the end. So this is the only node present in a linked list, so we have to remove first node from the end. So in this case, when we move fast pointer by one step, so initially both slow and fast pointer points to the address of this node. So let's say slow and fast pointer, and we move fast pointer by one step, then after that fast pointer points to null, and when we do this operation it will throw null pointer exception. So to avoid this, so this is the special case, we what we do is we check if fast equal to null. So we have to remove the node, only node present in a linked list. In this case, simply return head dot next. So head dot next is nothing but, I mean, in this case it will return null. So it will simply return null. So this is the special case, and this is the handling of this special case. Now let's talk about the time and space complexity. So the time complexity of this approach is O(n), and its space complexity is O(1). And also I'll share the code link. I'll mention the code link in the description box, so please make sure you check the description box. And that's it for this video tutorial. For more such programming video tutorial, you can subscribe our YouTube channel. You can visit our website, which is https://webrewrite.com. Thanks for watching this video.